Hello, our team members are Elliot Udell, Mikayla Quinn, and James Wagner. For our final project in ME 348, we determined coefficients of friction for 5 unique surfaces using an accelerometer. We will begin our presentation by discussing our hypothesis. We will then explain our experimental methodology. Next, we will go over our data analysis. Finally, we will review our results and draw conclusions.
In conducting this experiment, our team used 5 unique materials. These materials are plywood, aluminum foil, printer paper, parchment paper, and a cotton t-shirt. We also utilized an accelerometer in order to gather our data, which we used to calculate their coefficients of friction. The hypothesis of this experiment was that each material that we test will exhibit a unique value for its coefficient of friction. To further our hypothesis, our team ranked each of the 5 materials 1 through 5, where 5 is the highest coefficient of friction value. We assumed that aluminum foil would have the lowest, followed by printer paper, parchment paper, plywood, and cotton would have the highest coefficient of friction value. Our null hypothesis for the experiment was that each material would have the same coefficient of friction value. To test this hypothesis, our team first decided to construct a simple plywood ramp with a measured angle of 49.5 degrees. Once this ramp was constructed, we could easily cover the surface of it in whatever material we wanted to test the coefficient of friction of. We then would drop an iPhone down the ramp from rest and record its acceleration data. We could then export this acceleration data into Excel for analysis. Before actually analyzing our data, we first have to come up with a mathematical equation to solve for the coefficient of friction. After summing the forces in the x and y direction, we can come to the conclusion that the coefficient of friction equals the tangent of the ramp angle minus the ratio of our acceleration to gravity times the secant of the ramp angle.
There are 3 forces acting on our accelerometer as it slides down the ramp: friction, gravity, and the normal force. If we use Newton's second law to sum forces in the direction down the ramp, we find that the sum of forces is equal to g times the sine of theta minus the frictional force. We can rearrange this equation and solve for the coefficient of friction, and we get mu equals the tangent of theta minus the quantity of a divided by g times the secant of theta. Everything in this equation is a physical constant except for acceleration. Next, the accelerometer measures each individual acceleration in the x, y, and z dimensions as shown on the picture to the right. What we want to plug into our equation is the combination of the x and y magnitudes. The z acceleration is not needed to calculate the coefficient of friction, as it is perpendicular to the plane of motion. The magnitude of the x and y components combined can be plugged into the equation shown, mu equals tan theta minus a over g secant theta, to find the coefficient of kinetic friction. While processing our data, we must account for the fact that accelerometers cannot measure gravity. The magnitude shown while the accelerometer rests on a table is 9.81 meters per second squared upward. This is due to the effects of relativity, where the accelerometer cannot differentiate between gravity and a constant upward acceleration of magnitude g. As a result, we need to adjust the readings that the accelerometer gives us while it falls down the ramp. In the xy plane, the accelerometer reports a magnitude equal to g sine theta upwards minus the acceleration down the ramp. To isolate our acceleration down the ramp, we need to subtract g sine theta from our measured value and then flip the sign of this value. With this new magnitude, we can plug that into our equation mu equals tan theta minus a over g secant theta to find our measured coefficient of friction.
After exporting both the x and y components of the acceleration to Excel, Our first step in the analysis process is to calculate the magnitude of these accelerations per time increment. Once all the magnitudes of the accelerations have been computed, we then want to calculate the means for each time trial. Since there were 5 time trials total per material, we then want to take all of those calculated means and then average those as well in order to get the mean of all of our means. Once we've finally calculated the mean value for all of our measured acceleration magnitudes, we could then plug that value into this equation on the right and finally solve for our coefficient of friction.
For our statistical analysis, our group completed a student's t-test to determine our acceleration population mean interval. We used the following equation. Population mean is equal to standard mean plus or minus critical value times variance over the square root of our number of data points. Our critical values for each of the materials was 2.77644,511, and our population mean intervals are displayed in the chart. To create a visual representation of our population mean interval, we created a Students T PDF for each unique surface. From our statistical analysis, we obtained a range of coefficient of friction values with 95% certainty. For printer paper, the average value was 0.224 plus or minus 0.0107. For parchment paper, the average value was 0.1784 plus or minus 0.0084. For plywood, our average value was 0.257 plus or minus 0.039. For the cotton t-shirt, our average value was 0.4805 plus or minus 0.0618. Finally, for the aluminum foil, our average value was 0.36469 plus or minus 0.0566.
Based on this bar chart shown here, we can confirm our hypothesis in that saying that each material exhibited a unique coefficient of friction value.
While comparing our relative rankings as predicted in our hypothesis with those found from our results, we found that 3 out of 5 of our predictions were incorrect. While formulating our hypothesis, our group predicted that aluminum foil would have the least friction, followed by printer paper, then parchment paper, plywood, and finally cotton. However, after testing, we found that the material with the least friction was actually parchment paper. Aluminum foil, which we had predicted to be the smoothest material, tested as the second highest friction material. When considering this data, it is important to remember that our sample size is small. Due to the time-consuming nature of our data analysis, we only performed 5 tests for each material. For more accurate results, many more tests would need to be completed for each material. However, given the consistency of our data at an evaluation of 95% confidence, this data gives a reliable outlook into the coefficients of friction for these materials.
In conclusion, our team hypothesized that unique materials have unique coefficient of frictions. We predicted that cotton would be the highest friction material and that aluminum foil would be the lowest friction material. To test our hypothesis, our team constructed a ramp with a 49.5 degree angle, and then we covered the ramp with the material in question and slid an iPhone down the ramp. Using MATLAB Mobile, we finally collected data and exported it to Excel. Next, we used the student's t-test with a confidence interval of 95% to determine the most accurate readings of acceleration down the ramp when it was covered in each material. And finally, we took the acceleration data evaluated from the student's t-test and calculated coefficient of frictions for each material. The results confirmed our hypothesis that each material would have a different coefficient of friction. However, our expected ranking was incorrect. The results indicate that from highest to lowest friction, the order is cotton, foil, plywood, printer paper, and then parchment paper.